we conclude our discussion of relativity by looking at what's called the relativistic energy. Now, we talked about relativistic momentum in the previous section. This section, we're dealing with the energy of the particle. So the total energy of an object is equal to gamma, and the Lorentz factor, times the rest mass of the object times the speed of light squared. So gamma mc squared. Now, the total energy of the object is actually composed of two parts for relativity. There's what's called the rest energy of the object and the kinetic energy of the object. So the kinetic energy, of course, deals with speed, if you remember from last semester. Kinetic energy is the energy of motion. So where does the speed come in? Because the speed of light is a constant. Well, gamma has a speed in it, if you recall. Gamma is 1 over the square root of 1 minus the speed squared over the speed of light squared. So that's where gamma comes in. Gamma, again, goes anywhere from 1 when there is at rest, when the speed is 0, to up to infinity, approaching infinity. So if the speed is 0, if the object isn't moving, gamma is equal to 1, and we end up with what's called the rest energy of the object, shown here in red. E naught is the rest energy. It's just equal to the rest mass of the object times the speed of light squared. Now, this is probably the most famous equation to come out of the special theory of relativity. Although, as we've seen in the previous videos, many different equations have come out. Time dilation, length contraction, the relativistic momentum, and so on. But this is Einstein's most famous equation, E equals mc squared. What does this mean? Well, this means that the speed of light squared, which is a constant, remember c is a given constant, is just a conversion between mass and energy. Right? C is a constant, so it doesn't change. So when you change the mass, you change the energy of an object. No mass means no rest energy. It simply means that things with matter, things with mass, have an intrinsic energy to them. So this really unlocks our understanding of nuclear power. In nuclear fusion, light atomic nuclei are smushed together in the sun, for instance, in the nucleus of the sun, are fused together to form heavier nuclei, but there's a little bit of missing mass that comes about from that reaction. The amount of mass that's missing when you plug into this equation tells you how much energy is released by that mass. So mass and energy are equivalent, which is nice, right? That's nice. Mass and energy are equivalent. We can turn one into the other, not easily, but one can become the other. And we see this in particle physics. If you have a high enough energy photon, you can spontaneously create a positron and an electron. You can create mass. Or we'll talk about what positrons and electrons are later on this semester. So objects with mass can create energy. Now, the mass that is created in nuclear fission and nuclear fusion is usually a very, very small amount of the mass of the object. So if you have a big old uranium-235 nucleus and you fission it, if you put it in a bomb or put it in a nuclear power plant and you break it up, the daughter nuclei that come out, the resultant nuclei, if you weigh the mass, there's mass missing. You start off with a heavier nuclei than the sum of the nuclei you end up with. That missing mass goes into energy. It's like, well, what energy does it go into? It just doesn't. What is energy? Well, in that case, it goes into the kinetic energy of the particles. The particles, when you fission an atom, they get excited, they fly away at high speeds. That's thermal energy. Right? Average kinetic energy is a measure of the temperature of an object. So you create heat. Now, if you have actually a rock, and I certainly don't recommend doing this, if you actually could hold highly concentrated uranium in your hand, it would feel warm. The recent movie The Martian had a plutonium core that they use as a power source, but when the astronaut's trapped on Mars, he uses it as a heat source because it produces heat, which then can be converted into electricity. So this is the rest, and again, that's the rest mass. So particles without mass, like photons, have no rest energy. Any particle with a mass has rest energy. Now, this is the total energy of the object. This is the rest energy of the object. So what remains is the energy of motion, kinetic energy. So if we take the total energy and we subtract the rest energy, we end up with the relativistic kinetic energy. So the relativistic kinetic energy is the total energy minus the rest energy. So it's gamma mc squared minus 1 mc squared is gamma minus 1 mc squared. So this gives us the relativistic kinetic energy, and again, the velocity is in the gamma term. And hopefully you can see that when the velocity is 0, gamma is equal to 1. When gamma is equal to 1, 1 minus 1 is 0. So there is no relativistic kinetic energy when the speed is 0. As the speed increases, you end up with this. Now, at low velocities, this relativistic kinetic energy should give you the same equation or same result as the classical kinetic energy, right? When you're talking about the speed of a baseball, you should be able to plug it into either equation to come up with almost identical results, barring, numbers way out in the long decimal places. So for baseballs, why use relativistic? Why go through the complicated calculation of gamma and so on? It's not necessary. The classical interpretation of kinetic energy works just fine. But when you're dealing with really small objects or traveling at really high speeds, or even large objects traveling at high speeds, appreciable to the speed of light, you have to use the relativistic kinetic energy. And then finally, the equation shown at the end of this chapter, the total energy of an object squared is equal to the momentum times the speed of light squared plus the rest energy, mc squared, which we have up there, squared. So this has an interesting result, which we'll talk about. We talk about photons and particles, subatomic particles later on. Energy has two sources. There's a rest component to the energy, right? C squared is just a mass. Sorry, c squared is just a constant. You multiply it by the mass. The mass here is the rest mass of the particle. This is the momentum. Momentum also includes the rest mass, but includes the motion, the velocity, the speed. So this first term talks about the motion energy of an object. The second term talks about the rest energy. So if an object isn't moving, right, if the object has no motion with respect to the observer, P is 0, this becomes E squared is equal to mc squared quantity squared. Take the square root of both sides, we get E equals mc squared. What if a particle has no mass, like a photon? Light has no mass. Well, the mass is 0. But what this shows, and while particles' relativistic momentum has mass, what this shows is if a particle has energy, it has momentum. So photons have energy, right? You can get sunburned from a giant ball of plasma 93 million miles away. There's definitely energy in sunlight. That energy means that light has momentum. And we can talk about scattering and things like that later on this semester. So this concludes our discussion of relativity. It's just one chapter out of this textbook, but so much is still being learned about special, and we didn't even talk about Einstein's theory of general relativity, which he came about with in 1915, which talks about accelerating reference frames, non-inertial reference frames. So Einstein really, by himself, revolutionized a huge field of physics. The rest of the semester with modern physics, we're going to be concentrating on quantum mechanics, talking about the mechanics or the physics of very small objects, atoms and things like that. There's no one person that really worked on all of that quantum, although there are some famous names you might be familiar with, Schrodinger, Bohr, and so on, Heisenberg. Relativity was really Einstein's baby, and we owe him a great deal for revealing this part of the universe to us.